can assist you or tutor you more. If you have more questions, just email me. 9 over here. The uniform crate has a mass of 150 kg. If the coefficient of static friction between a crate and the floor is μs equals 0.2, determine whether the 85 kilogram man can move the crate. The coefficient of static friction between his shoes and the floor is mu equals 0.4. Assume the man only exerts a horizontal force on the crate. Alright, so for this type of problem when somebody is pushing something else, like the previous question 11, right, the pulley system with the human being, it's always good to divide the entire system into two and then draw the FPD, free body diagram, separately. So you can see over here, right, I draw the one for the person. Didn't want to try drawing a real person pushing something, right? My artistic skills is very limited, so use your imagination. And over here, here's a box, and drawn all the forces on it, right? The center of mass, the force over here. So the person is pushing on the force, pushing onto this thing over here, right? The box, which means the box is experiencing a force pushing onto the box, right? But for the human, the box is pushing the equal and opposite amount of force to that person, right? Newton's third law. And the foot over here, these two we can simplify as to one. Friction force, since this is pushing the human this way, the friction is bringing him forwards. And over here, since it's being pushing to the right, the static friction force is pushing the box to the left. Alright, so now we understand the free body diagram. Let's get started. To system over here. So first, let's do the person part. So it's 85 times 9.81 meter per second squared, right? This equals to, well, this is the sum of the forces, this is the sum of forces into the y direction over here, right? Equals 833.85 newtons, right? This is the amount of force that the person exerts on to the earth, right? This is the weight of a person, which also happens to equals to n, right? Because this force is the only force that's counteracting the normal force, right? Two forces into the y direction. And then now we can use some of the forces in the x direction. Going right to is the positive, right? So is the normal force, which is normal force, which is we calculated 833.85 newtons, right? Times the coefficient of static friction of the feet, of the shoes in the ground, which is 0.4, right? And that equals the amount of P that the person can push, right? And that equals 333.54 newtons. So you plug everything into your calculator. All right. So now we have calculated what the person can push onto the crate, which is the big part for solving this equation over here, right? So over here, we can use some of the forces again into the y and x, right? Y and x. So let's say the sum of the forces into the y direction in the box system over here, right, going upwards is the positive, equals to 0. So that means 150 kilograms times the acceleration due to gravity, and that is equal to, because this is the only other normal force that's counteracting this force over here, which is and the normal force at box, right? And the normal force should give you 1,471.5. Let's call that, the weight of the box, right, over here. And then we can use the normal force of the box times the coefficient of static friction, calculate the friction force, which it should give you 294.3 newtons, right? This is the friction force over here. So if we do compare these forces, right, the force that the human can exert, right? He doesn't have to put all of the forces, but he can if he want to try his full efforts, right? 150 force, right, is bigger than 294.3, right? So once this man is pushed over the let's just say this number over here, pushed over this box will start moving because that is all the force that this force can, go against the human pushing force, right? If we looking at the graph the book draws, it's this friction force is going up and up and up and up and up and up and boom, and hits a spot, and then it will drop. And this is the area where the object starts to move. And then as speed goes on, and then it will just the friction will stay constant, right? So this is friction force. This is the friction force, and this is the time, right? So over time, by the amount of force exerts, right, the amount of and also amount of force the person exerts, right? Not really the time, sorry. It's more about the amount of forces exerts, right? It's this one over here. So now we know that the person has the ability to push the box. Now we have to consider in real life situations whether the box will tip over or not, right? Will it keep going, or will it, fall to the ground? So to do that, and that is why I draw the normal force over here, because I don't know where exactly the normal force would be when it's being pushed, right? When it's being pushed this way. Because, when it's tipping over, it's all about on this point, if, which is say if the box is tipping over, all the normal force is going to be one corner, right? It's not going to be perfectly in the center when it's like resting, right? This is about to move kind of a situation, right? We're just hitting dynamics. Right? Not there yet, but close. We're hitting the connection, the bridges that build these two together. So to do that, we can use the moments, right? Because tipping over is a rotation kind of a movement. So we can use the moments at this area over here, right? It cancels this force, friction force, and cancels the normal force over here, right? We can just count right in the middle over here. So that would be in the normal force of box, and it's some distance over here, right? Times x. Let's just say x. This, and this is going to move into a counterclock direction, so that's positive. So minus the p force times 1.6 meters, and this whole thing gives you 0, right? And plug everything into your calculator, right? We already find what p is. We already know what n box is. X bar, x average, or distance between the center point to where the normal force it should give you 0.363, and that means 3.36 meters, right? Is much. It's about half of the size of the 0.6 meters, right? Which is half of the distance of the base of this box over here. So that means this force, which I kind of draw it right, it's about this area. So that means this box will keep moving and not tip over, right? The only reason, the only situation when the box will tip over is when n is equal or bigger than the half distance over here. That's when we know. So if this number is like 0.61, then we know that this box will, tip over instead of moving forward, right? So, this kind of a box situation, it's always good to check the two scenarios, right? Whether it will tip over or it will keep moving or stop, right? Moving or stop, we just compare one force, and then we'll have to do another one using Moment's equation to find whether it will tip over. So yeah, hopefully this question was helpful, and give it a like or subscribe. It's a relatively new channel. Hopefully your contribution would really help this channel to grow and letting more people to receive help. So yeah, good luck on your revisions. Good luck on the course. I'll see you in my future videos. Bye. If you have more questions, specific questions you would like me to do, please comment in the comment section down below.